Hi, teacher. Today we'll talk about topic 5, numeric integration. By the way, my name is Domington. My student ID is 22161077. First, let's have a look through the outline. We have rectangular rules, we have trapezoid rules, and we have Simpson rules. First, rectangular rules. We will consider an interval split into n stripes. It will have the following x coordinate, like x0, x1, x2, and so on. It will corresponding to the y coordinate. The height of each rectangle is defined by the middle point of the y. The height of each rectangle is defined to be the y coordinate at the middle point of each pair of x coordinates. And the width is h, is where h is b minus a overall divided by n. For a and b is the limit of integration. So we just have the total area of all rectangular. That's the main key point of this rule. Here's the formula. Next, we will have an example for rectangular rules. Let's say we have a x squared integral from 0 to 2, and we have a 5 stripe, and we have first we have to find the width is equal to 2 minus 0 divided by 5. We got 0.4. Next, we have to find x1. X1 will be a plus h divided by 2. So we have 0.2. From the second x, we just have to take the previous one and plus h. Here's the table. I already done it for you. X here, like I just said, from the second x, we just have to take the previous one and plus h. So we have x2 is equal to x1 plus 0.4, and we have 0.6, so on. Fx is where you just plug in the x you just found into the function here, like x squared. So 0.2 squared is 0.04, 0.6 squared is 0.36, and so on. We come back to this formula here, and let's just put everything we have in. H is 0.4 multiplied by each of x fx here, and we got 2.64. Yeah. Next is advantage and limitation of rectangular rules. Why the rectangular give a approximate or region with roughly constant gradient, like from x3 to x4, but they are less accurate when the gradient change rapidly. When the gradient change rapidly from x4 to x5. Next, we have trapezoid rules. It's just the same as the rectangular rules, but we also consider interval split into n stripe. It will have the following x coordinate, x0, x1, x2, x3, with the corresponding y coordinate. The height of each trapezium is a horizontal width given by h, where h is b minus a overall divided by n. where a and b is the limit of integration. Since the width of each trapezium is given by the y-ordinate at either side, so at 2n of the integral, you have to multiply by well, by a half. Example for trapezoid rule. It's just the same problem, but it will be a bit different. Like from xi, you just take the previous one and plus 0.4. So we have 0.8, 1.2, 1.6, and 2. Whereas 0 and 2 is the n as the 2n a and b of a integral. So fx is just plug in multiply we just square of each of xi here. Formula again. Please remember trapezoid rule, so you have to multiply by half of each 2n. Like I wrote here, like 1 half of multiplied by 0 and 1.5 multiplied by 4. It will give a different solution because trapezoid rule is much more accurate than rectangular rules. But there's also a limitation to trapezoid rules. For decreasing gradient from 1 to 3 on the graph, it will give an underestimate. This will be the white part you see here. Like, and for the and for the increasing gradients, like from x3 to x5 here, it will give an overestimate, which is the part where it's just over the black line here. It will give an overestimate. Next is Simpson's rules, which is considered is the most accurate of those three. Well, we also consider into n strike, but this is a special one, so we have to n have to be an even number. It will have the following x ordinate x0, x1, x2, and corresponding y ordinate. And a parabol is mapped throughout the integral, like x0, y0, x1, x2. This will be repeated for the whole interval, mapping each subsequent ordinate pair with parabolic curve. The process of doing this involving setting up simultaneous equation of form y equal to ax squared plus bx plus c, and resolving for a, b, and c. While tidiest, this is achievable and yield a series of quadratic functions which can be ready to be integrated into. Here's the next is example for Simpson rules. Also, this just the same one. We have the width. Oh no, the split is have to be an even number, so I choose 4 split. Oh, four stripe. My bad. We have the width is b minus a overall divided by the stripe. We got 0.5. We plug in everything we have, like the last two times. Um, and lastly is the formula. H divided by 3, 0.5 divided by 3, we multiply by H of here. A small tip to help you remember this Simpson rule is 1, 4, 2, and so on, 4, 2, 4, 2, 4, 2, 4, 2. But the last two is 4 and 1. Next is advantage and limitation of Simon rules. This will give a better approximation than the previous two methods. However, since 3-point require a defined parable, an even number of stripes is required for the formula to work. So if you have an not even number, an odd number, so this will not work. Accurate. The accurate of any of these methods is depend to a certain extent on the function itself, but any of the method can be improved by increasing the number of strikes using for given number of strikes, like for the same function here. If we increase the strike, so the percentage of error will decrease. And that's all. Thank you for spending. Thank you for your time. Thank you for listening. That's everything I wanted to share. Thank you, teacher. Mình hai phút. Hai điểm